Good morning, chemistry students, or afternoon, or evening, or middle of the night, whatever it might be. I'm going to give you a quick overview of the follow-up information that might be helpful for somewhere in the Rainbow Lab that we did right before spring break. This is a little bit of follow-up information. So I want to point out that this is the last learning goal in this unit, 3.2, all about electrons. Bare minimum, you need to understand how different electrons are from the protons and neutrons here in score 2. And I'm going to give you a little bit of information to further explain their location. Score 3 is really about what you saw happen in the lab somewhere in the rainbow. This has to do with energy and jumping between levels, so I'm going to give you some information about that, as well as there's information in the reading that was assigned as follow-up to the lab as well. Please be sure to do that. And then also related to this lab is really score 4. Knowing how to do those tests that we did. They're called flame tests, which I'll talk about, and atomic spectrum data and what that means. Again, you saw all of these things in the lab. A lot of this, again, is also reviewed in the reading that was assigned. So again, please do that and answer those questions. First of all, here is our simple model of the atom that we think of today. We did a lot of work with what's going on in the nucleus in the last section, with protons and neutrons. And this section deals specifically with these tiny little particles that are outside of the nucleus, outside of the center, called electrons. This particular model is of nitrogen, so there'll be the correct number of protons and neutrons in the middle here for nitrogen, and the same number of electrons as protons out here to make it balanced, because it is an atom, so the charge needs to be neutral. The thing that you need to understand now is not only are electrons outside of the nucleus, but they are found at distinct distances away from the nucleus. So this first ring that's depicted here, again, this is just like an imaginary line. This is a location very near the nucleus where you will find electrons. A little bit farther out, again, look, there's another region of space where you might find electrons. These are called energy levels. And that's really what we're going to focus on. Now, in addition to energy levels, within each level are different orbitals. So within the level, there is a region of space that you would expect to find electrons. Atoms are most stable if their electrons can be as close to the nucleus as possible. There's only so much room there. For example, this first energy level only has room to hold 2 electrons. So since nitrogen has more than 2 electrons, some of them have to go then to the next energy level. That level will then fill up first before any electrons may need to go to the next level out for atoms that would have more electrons. It is most stable, again, for them to be as close to the nucleus as possible. It's a low energy, stable state for the atom to have their electrons there. Like I said, within each of these energy levels are different orbitals. So we're going to focus mostly on electrons, but I'm going to show you a slide of what this looks like. Here are the different types of orbitals that you can find within the energy levels themselves. And they're labeled S, P, D, and F. And they are given different letters to distinguish the fact that they have different shapes. An s orbital is completely spherical. And there's only one way to orient a sphere in three-dimensional space. So there's only one possible way that an s orbital can be arranged. P orbitals, however, it looks like 2 balloons tied together, kind of. And so in three-dimensional space, which we know atoms are taking up and their electrons, there are 3 ways to orient a shape like this that would be different in three-dimensional space. So in p orbitals, there are 3 different ways that it can be arranged. So there are 3 placements of p orbitals. D orbitals are a little bit more complex, and so because of that, there is even more ways to arrange them in three-dimensional space. There are 5 different ways. So in energy levels that have d orbitals, there could be as many as 5 different locations for them. And then f orbitals, even more complex still, so there are 7 ways to orient those in three-dimensional space. And it's a different orientation that orbitals need to be able to hold electrons. The other thing that might be interesting to know to understand how all of this works is in each orbital themselves, here's an orbital, 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 you can only have 2 electrons. No more than 2 electrons can occupy this space. And that's because they need to be completely distinct. And the last kind of uniqueness about electrons, aside from their energy level and what orbital they're in, is which direction they spin. And there's only 2 ways to spin, clockwise and counterclockwise. So you can only have 2 electrons here, one spinning clockwise, one counterclockwise, same way here and here. They cannot occupy the same space doing the same thing at the same time. And so that limits the number of electrons that can be in an energy level, and that can be in an individual orbital as well. And so that's why there's this need to have different locations for those electrons to be located. So let me go back up to this slide. So again, energy level. This does not depict it, but within this energy level are orbitals. This particular energy level only has one type of orbital, an s orbital. The next energy level out, however, within that energy level, within that space, there are 2 different types of orbitals where you would find electrons. Now, the other thing that you did in the first lab is realize that this whole region that is occupied by electrons is called an electron cloud. And you can think of it as a cloud because it's kind of a fuzziness, because we're not exact sure of their location, because the other thing that's kind of interesting about electrons is that their location is all based on probability. Again, like I said, most of the time, electrons will be as close to the nucleus as possible. It's the most stable location for them. But just like probability, any one electron could be anywhere else around the atom. And that's a really weird thing about the theory that we use to describe atoms. You made a graph that probably looked like this in the very first lab that you did when you were locating electrons around kind of a central location when you drop the felt tip pins. What this means then is for that atom that you were modeling, or the one that's in this graph right here on the green line, is that the most probable location for the electron in that atom is in the 1s orbital. This would be in the very first electron level, the very first location outside the nucleus. Other electrons, if there are more electrons in an atom, this shows their probability of where they are likely located, and then again more. So notice the probability goes down for individual electrons as you get to different locations, but it doesn't go away. It is possible those are still there. So again, the location of an electron we can predict where they probably are, but we cannot pinpoint them because of their behavior. Very interesting. Later, there's another follow-up assignment to watch some videos that hopefully gives you another idea of how to think about this, and again, you might find that kind of interesting. Okay, here's what's going on with Somewhere in the Rainbow. When you put compounds in the flame and they gave off certain colors. Here we have the energy shells again, and these black dots represent electrons. So we're going to start down here. This would be kind of like number 1. This is the current state of the electron before you charge it up with the heat of the flame. Well, that energy, which is depicted here as a photon, this is like a little packet of energy that you were given it, it absorbs it. And because it absorbs it, it increases its energy level, and then it has to jump out further away to match the energy that it now has. Because these energy levels, as you go out, get higher. So it briefly jumps out to a higher level, because that's what it has now. But like I said, it's not stable for it to remain there. It's more stable to go back to its home base as close as it possibly can to the nucleus. So then we go up here to number 2 then. Quickly what happens is that electron goes back to where it is supposed to be located, but it has to get rid of that extra energy, and so it emits it again as a photon. Again, a photon is a little packet of energy, and when you get lots of photons together, we depict those and process them as light. The specific amount of energy that get combined in all these photons is what gives us the color of light that we see. So the electron emits or absorbs the energy, changing the orbits. And again, this happens briefly, gives off that light, returns to its normal state. And again, we see that energy release as the colors coming off of the flame. So here's a picture of what you guys did. In fact, you probably tested most of these. I would guess that this one is probably sodium. It's a very violet, light purple color. Hopefully you saw that. This one likely is copper. This is one that a lot of people are familiar with anyway, giving off green light. This one, I would guess, likely sodium, very orange light. Here's kind of a reddish orange, which is typical of strontium, which you may have seen. This one is probably my favorite. It is lithium. It gives off a very bright fuchsia color. I don't think we tested this one. I don't think we tested that one as well, but I'm pretty sure these colors should look familiar to you. In addition, you used a very simple type of spectroscope, the rainbow glasses, to give you the specific frequencies of color that were coming off the flame that you saw. This happens to be an electrified gas. Gases also, in the element form, will give off a certain color. For example, you see that on a common basis in neon lights. We electrify that gas, causes the electrons to jump around and give off energy, and gives off a certain color. Well, if we run that through a spectroscope or rainbow glasses, very high-tech rainbow glasses, this is what we would see. The distinct colors of photons given off by this element that are all broken up into their specific frequencies. It's the combination of all of these again that give us this kind of violet color is what it looks like on my screen. This is called an atomic fingerprint. This is specific for this particular element. Every single element has a very specific atomic spectrum that will be given off when its electrons give off that extra energy, and you separate out those frequencies or those photons. You can use this then to identify an element because it is distinct and unique for each element. It's kind of like a human fingerprint is distinct for each human, and we can use those to identify individuals. So you got a little bit of observations of that with the rainbow glasses. Again, I think that's the end of the slideshow, but please be sure to do the reading and then watch those short videos about how to think of electrons and how they are quite strange and unpredictable with their location, and then you should be ready for Section C quiz, I believe, and then Unit 5 tests as soon as you're ready. See you later.